to arrows in Haskell. This talk was also given yesterday at the Functional Reactive Meetup in Helsinki. But I need to re-record it because the screencast was not switched on yesterday, so it's of a much higher quality video with the screencast. So that's the reason why you see a different talk than was given yesterday. So a different recording of the same talk. Okay, so this talk is inspired by Paul and his really great blog post. And the goal here is to create this kind of OR gate using these negative AND gate only. And for that we are going to compose an inverter, two inverters and a negative AND gate, and then you will end up with a OR gate. And we are going to do that in Haskell. And basically in Haskell this circuit is a data type, and in this case this circuit is just function application. So if you have a Java background, then you can imagine that this circuit is an object that has just one method called apply, and that method has this as an input, so it takes two booleans and it outputs a boolean. So basically in the Java world this negative AND gate would be just a class. Actually it could be a static class, and then it would be this function. But more generally it can be an object, and the object can have a state. So more generally this circuit can be stateful, so it doesn't have to be a referentially transparent function. And in Yampa that's the case, that these kind of signal functions that you will see in Konstantin's talk, these circuits are actually not really referentially transparent. Well, in some sense. So they have a certain kind of memory built into them. Okay, but let's see how we can create this negative AND gate in Haskell. So you see here that if you apply true, then you get false, and if you apply false, then you get true. So in Haskell, function application is just a single space. So for example, if we take the wire here, that's just the identity function, then we get true. And this is here the identity function that just takes something and returns the same thing. It takes anything. This is a type parameter. pretty much the same as in Java. In Java you have also type parameters for functions as well. Okay, so I have already talked about the wire, which is also a circuit. And we also need a splitted wire because we want to create an inverter. And this inverter takes a splitted wire. So a splitted wire is this part of this inverter, and the second part of this inverter is this negative AND gate. So but let's see first what this splitted wire does. A splitted wire takes a boolean and basically it basically doubles the input. It just splits the input and sends the same to the output, both of the outputs. So it just has the same signal on both outputs. But what happens if we, for example, take a wire and an inverter okay, and I put in true? Well, then you see that actually the outputted value is on the left side is the same as the input, but on the right side it's just the opposite, because we were doing this kind of fan out operation, and here we were using an inverter. So basically this part of the circuit was replaced by an inverter in that case. So then one part of this resulting circuit block is inverted and the other part is the same. So this is what you have seen here. Okay, and well, we can create this inverter by composing a splitted wire with a negative AND gate in a serial way. And as you have seen, an inverter is just inverting whatever it gets. So then we need also a parallel composition, because we need a circuit that takes two inputs and outputs two wires. So it has two outputs basically. Two input, two output. Because our OR gate has two inputs and those two inputs will, because this is how our OR gate is going to look like. We will need this part here, and we're gonna put that part here, and then we will need this negative AND gate, and we're just gonna plug this negative AND gate to the right side of this circuit block, and this circuit block consists of two inverters which are composed in this parallel way. So let's see what this does. So parallel inverters is doing just an independent inverting of the inputs. So basically they are just happening at the same time. So in this way you just compose two functions in a parallel way, or not really functions, but anything that can have an input and an output. So it can be some kind of stateful state machine, for example, like a stateful object or something in more general thinking. It doesn't have to be a referentially transparent function. And we can have this OR gate by composing this parallel inverter with the negative AND gate, because the parallel inverter outputs two booleans and the negative AND gate takes two booleans as inputs and outputs a single boolean. So let's see if that is gonna give us the needed OR gate. So for example, an OR gate should output false if we put on both inputs false, and if we make any input true, then we get true. And it's not an exclusive OR, so we should get also true if both are. Okay, so this is really nice, but we can do this even nicer, in an even nicer description, by using this notation here. And this notation is used very heavily in Konstantin's talk, because it's a much simpler notation to describe the same thing. So this notation here is automatically translated into these operators. So this notation was invented about 15 years ago, and the reason is because if you have complicated circuits, then you don't want to use these sort of combinators, sort of basic combinators, but you want to have these bindings here. For example, this M1, M2, and then you can build up some more complex circuits from simpler circuits. And you can see that this also has the same behavior as the other OR gate. It's just a different notation. And it really corresponds to this diagram here, because you have an input here, which is A, and then you split that input. So this here corresponds to the splitting, because you have one A here and one A here. So you see here like one A here, one A here. So here is this A, and here it gets split into 1 and then 2, and this is this splitting part here. And then you pipe this tuple, this splitted input, into this negative AND gate, which is here. And we did this piping here when we were doing our inverter. So we splitted the wire and then we were piping it into this negative AND gate. So this part of the story is exactly what we wrote here. and then we got this inverter as an output. And then we do exactly the same for the lower branch, for B, and then we get two inverted signals or two inverted inputs. So both of these are inverted because of this, and then these inverted signals are then piped into this negative AND gate again. And this is what we were doing here. So we have these inverted signals here in a parallel composition, and then that parallel composition is then piped into this negative AND gate. So this is the bit that corresponds to this kind of third line here, this syntax here, and it's almost a one-to-one correspondence. You can almost draw the lines how these things correspond to the circuit diagram here. So you could draw a line from A to this A, and then that goes here, and then this then goes in here, and then that goes here to the output.